Okay, so the talk is about the Raman fields and the BRST of N equal to particle. This is the table of contents. I will first tell you about the worldline formalism, and I will convince you that we can describe half integer spins particles using supersymmetry. As a second part, we will see the n equal 2 and n equal 4 case, where n stands for the amount of supersymmetry that you will have. And I will conclude by telling you more in detail what I'm interested in at the moment. So these Raman fields that we will not consider in twisted K theory, but just as closed P forms. Right, so, and apologies for, because the talk is very basic and also not very mathematical, it's about more fundamental physics. Right, so we know that Wigner classified irreducible representations, which are also unitary for the Poincare group. And these were classified according to the mass, which is a Casimir for the translational part of the group. And then we have this pseudo vector, which helps to classify as well for the Lorentz part of the group and Lorentz group. Here momenta and M are angular momenta. So this is a second Casimir, and therefore you can classify all the irreps by the mass and the spin. So I can, for example, study a scalar particle by writing down an action functional along the word line. I have P nu x dot x dot nu. Where I can think of P and X and P as being fields, maps from the interval, the real line interval, the real line, to cotangent space. So X lives in the space, let's say cotangent space to Rn. X lives in Rn and P lives in the fiber to Rn. It's very easy. So this is action for the scalar massless particle. It has a very simple symplectic structure as well. You can write down the canonical boson brackets, which are very easily seen to be. Right. However,
so normally it would start like this. So x dot mu plus m squared in the second order formalism.
But I've already thought I will write down the Lagrangian as the symplectic one form minus the Hamiltonian also.
Yeah, okay, because that's the first order.
Yeah, because the symplectic structure is kind of important, and then I would also like to point out that one should take care of the reparametrization invariance, because you don't want your action to depend on the parameter that you choose for your interval here. So we can introduce a Einbein, it's called, can take care of this symmetry. So yeah, you can see, you can always set the I'm going to be 1, and your action has such a reparameterization invariance seen from these are the infinitesimal transformations. And then you will have the E transforms as according to the Lie derivative along the psi, your vector field, as a 1 form. Let's select this. Okay. Very simple, very easy. Now, people also observe that you can actually work with instead than with P, X, and E. You can think of them as the as carrying spinor indices. So you can think of P as an object carrying 2 spinor indices, X dot alpha, alpha dot, and then actually you can consider such a pair of spinors, lambda and lambda bar, which are conjugated. I mean, they are complex spinors. And integrate over your word line. So this, let me say, just this represents the word line represents the. It's not the trajectory of a particle, but if you consider the light cone, then your particle standing still in space-time will describe such a trajectory inside the light cone. So these are called light, or I mean, causality is respected. If it was moving like this, then it will not be causal. Okay, so that's very nice. You can think of your fields as having 2 spinor indices, and moreover, by calculating the equation of motions, so by setting the variational derivative of S with respect to the fields here to 0, and in particular with respect to lambda, you will see that P alpha dot alpha dot has to be 0, and the same is true for a complex conjugate. P alpha. But because also pi dot must be 0 from the equation of motions, then you will see that first of all, pi alpha dot can be a solution to this if it's itself given by a pair of spinors like this, because of the contractions between spinor indices. Since whenever you raise a spinor index, you are using the pseudo Levi-Cheat symbol, which is anti-symmetric, and these 2 are instead symmetric objects. I mean, have a bosonic statistic, they compute. So if P is this, then this one is solved. Moreover, since P dot must be 0, then actually lambda and lambda bar do have their own dynamics. In particular, they have to solve an equation of this type. Okay, and this is called the pure spinor particle. Okay, so far so good. I've just spoken about the very simple massless particles without a spin. But what about considering supersymmetry? Well, my point now is to show you that with supersymmetry you can actually you will actually have a Dirac spinor or normal spinor in your spectrum at the first quantized level. Okay. So you take that action above there and you supersymmetrize it. Which is actually also equivalent to extending your symplectic structure to an ortho-symplectic structure. So you'll have in let's say the dimensions, so that your fundamental form that you want to preserve now has such a structure, because it's zero everywhere else outside the diagonal, and these are 2 times 2 identity matrices. So basically you're assigning to X fermionic Grassmannian variable partner, and that's it. And then you have to take care of supersymmetry itself. So you have to write down the supercharge and yes, put it as a Lagrange multiplier. Yes, a Lagrange multiplier to your action. So we have X dot P again plus I psi dot psi, where psi will be your Grassmannian variables, minus E P squared over 2, and then minus I chi psi, I can write it, psi mu by mu, like this. So P squared is your Hamiltonian, will conserve the charge for translation, and this is will conserve the charge for supersymmetries. The supersymmetries infinitesimally have this form, which I'm going to copy. Epsilon now is another Grassmannian parameter, so the supersymmetry depends on epsilon. Then that psi. B is invariant, while E transform as 2i chi epsilon, and chi transform as epsilon dot, where dot of course means derivative with respect to tau. Right, so now you could ask yourself what will happen if you try to supersymmetrize this part, which is completely this maybe I failed it. I didn't say this, but this is an equivalent action with the other one there, because okay, we said this is a solution to this. Obviously, you can always say it was taken for E equal 1, so you plug E back and you substitute lambda bar here for P, so it's again exactly as what we wrote down on top. You have a question? So now we want to supersymmetrize this other equivalent action, because we should use an observation coming from this supersymmetrization for the next part of the talk.
Sure, can I have a question?
Sure.
I don't know if it's so the twister action, that was just 4D, right?
For dimensional.
Right.
Yes.
But those lambdas are unconstrained, right?
But it can be also 10-dimensional, for example, for string theoretical reasons.
Okay, but then so in 4D lambda was unconstrained, right?
Yes.
And in 10D, is that pure spinor constraint which you need to impose on lambdas so that the 10D works, or
yes, yes, you're right. There is this pure spinor constraint also in 4-dimension, I think.
But no, but in 4D, in 4D, it's equivalent to being chiral, isn't it? I think if you're trying to solve the pure spinor constraint, you see that the chiral spinors already are pure, I think. Is it not?
Okay, could be.
Sorry, I can't really hear that.
Equivalent to it's like. So can you repeat it for the audience? Two chiral spinors.
Okay.
So
in 4D, just for the right X and P's, you just you sigma matrices, right?
yes, or Dirac gamma matrix. Yes,
Yeah.
because they come from the poly ones. Yeah, now I think so that that's the case. So in 4D they're not constrained, but yes, in 10D you have this constraints coming from the pure spinor. Thank you. Right, so we were about to see also supersymmetrization in the context of this pure scalar action. Right, on this. Right, so and you send x to x plus chi, where chi now are okay, I've already used chi, if I will use chi theta, I already add the Grassmannian variables. Then p to from lambda to lambda plus theta. And you send also your proper time, or I mean your time tau, to tau plus theta. And you substitute your partial derivatives with respect to tau into super covariant derivatives. No, sorry, plus theta here plus I theta d tau. And if you do all the substitutions with correct also parameters inside and integrate over d eta, using of course the integration of Grassmann variables is 1. Then your final result, you have to believe me here, I don't want to give you more details. Let's call this pure spin action. It's going to be then you'll have again lambda bar as before. Rho is just a Lagrange multiplier, so you can use the equation of motions for chi to set it to 0 again. You can also again use the P alpha bar is lambda bar alpha dot. Yes. And then actually, there's another symmetry. This action does not only enjoy reparametrization invariance and supersymmetry, but also another symmetry called the Siegel or kappa symmetry. That infinitesimally looks like this. So I'm going to write it down. Depends on the parameter kappa. Let's call it kappa. P theta alpha dot theta alpha. Then I will have one can check that this is really a transformation that leaves the action invariant. And now I'm gonna jump a little, and it's gonna be a bit of a leap. You should trust me that by gauge fixing such a symmetry, you can end up with with your psi from before, from the other action, that can be written in such a way, so not. Plus theta bar alpha dot Right. So in fact, you can do this. This is totally fine, and you can actually write your other Grassmannian variables as a combination of a pair of other variables, other spinors, where theta are again Grassmannians. So theta alpha, theta beta is equal to minus theta beta, theta alpha, while, and the same is true for the complex conjugate, while lambda alpha, as before, is symmetric under the exchange. Okay, so this is allowed. And now I will finally be able to tell you why.
Sorry, Eugenia, can I have another question? So this this supersymmetrization, it seems like worldline supersymmetry, right? RNS like, and then
Yes.
The kappa symmetry, that's usually present if we're doing Green-Schwarz like supersymmetry, right? The target space one. Is this?
Yes, and you have supersymmetry also in target space as well here. Yes.
And so here, just by doing RNS supersymmetrization, you end up having thetas which are also super partners in Green-Schwarz sense to X, or is that what's happening? Like somehow you get for granted target space supersymmetry?
I think it's imposed to be like that in this moment. I don't think it comes for free.
Wait, so does this action, this fully supersymmetrized action without the kappa symmetry being gauge fixed, does it also have Green-Schwarz like supersymmetry or not?
Now I'm not. I don't recall exactly what's the Green-Schwarz.
I mean, like maybe X going to thetas kind of thing, right? Like I'm thinking.
Could be. Well, the reference for what I just told you about is a paper by Sorokin and Volkov and another person from the 80s, I think, and it's about kappa symmetry and the particles.
Okay.
So maybe you can find your answer there.
Thank you. Thank you.
Right. So now, from this supersymmetrized action, they are all equivalent. Were supersymmetrized ones. Let's take this one, for example. You can start your quantization, so canonical of canonical type. You substitute your Poisson brackets with a commutator of observables. So this is what has been done first in a paper by Brink, Di and Howe. So you have this for some brackets, as I told you before. And then you have also these other brackets. I mean, this is for some brackets between the and these are, let's say, theta mu. So you see that there is Clifford algebra that wants to come out from here. Comes your operators, commutator of observables. And now that you have your this observable, this commutation relation, you can try to to find the states in your Hilbert space that would also satisfy the other equations, which are the other constraints, which are the p square on the ket, on the state. So let's call it. I ran out of Greek letters. And to see that. This will be your constraint. And a physical state must satisfy these constraints. And what I was observed is that there are two ways to satisfy this, and I represent the algebra. So there is a fermionic sector. Let's call it fermionic. Also for a particle, yes. Well, phi is exactly given by a Dirac spinner and a ket which depends on the momentum and will solve it's physical when it will solve p square phi equal to 0 and also this constraint. So basically, you will end up with a wave equation, and the slash of your spinner, right? Something like this. I'm not sure. Okay, so instead for the other representation, we could think about whether you can always set your gamma matrices to in pairs. Let's call them psi plus and psi minus, so where psi plus and psi minus, where they are defined like this, for example, where I runs from 1 to half of the dimension of your.
Could you rotate the camera, please?
Sorry?
Could you rotate the camera, please?
No. Okay. Maybe we can.
Thank you.
Okay, I hope you can see. Alright, so then you make such an assignation. You say psi minus behave like an annihilator on your ground state or on your highest weight state, while psi plus are generating all the states. So they are creators. And you will see that to solve this phi square on the state created by psi plus and psi dot p on the state, you can just form when you write it here. Okay, your actually this will also depend on p. It's 0 for the spin part, so you end up with 0 p. Then you have psi plus from 0 p, and then you have psi plus. Let's call it 1, psi plus 2 minus psi plus choose say 1 plus only 0 on P, which form your Hilbert space. And if you count it, this is 1 state, and this will be 2, and this is 1 again, which is the same as before. You had the 4 because this is 4 dimensions. So you have 4. I'm counting really matches. So you have two sectors. Good. So do you have questions now? How much time? Oh no, you have only 20 minutes. So now for the second part, I just wanted to briefly mention that there are generalization to n equal 2 and n equal 4, which are very relevant, above all because thanks to this worldline formalism, it was possible to compute scattering amplitudes for Yang-Mills theory, and also for gravity, linearized gravity, and also the vertices for the bosonic GH dilaton multiplet of supergravity as well. Okay, so now for the n equal 2 case, and if you directly start by with a BRST quantization of a theory that has massless particles and n equal to symmetry, it means that you're actually looking at Siegel explained this in his paper. Orthosymplectic of 1,1/2 times SO D. So you're looking at a representation of this algebra when you're doing BRST. So your algebra must be in the canonical path. Okay, let me write directly the commutators. So you have you have these are Clifford brackets. Let's call it psi bar mu, psi mu. So you have a pair of signs. Psi bar, as well as psi and psi at 0. So this is where the n equal to supersymmetry is displayed. Then for BRST, you need ghosts. A pair of ghosts is, for example, the following with such so these are bosonic ghosts for the psi, while for the p square equals 0 constraint, you need to work with fermionic ghosts C and D. And these are anti-commutators, these are commutators, commutator. Okay. Now, studying the BRST homology of this thing, one should note that there are vectors, because we just said that to n equal 1 corresponds spin 1 alpha particles. So with n equal 2, you can have spin 1 vectors. And something even more interesting is to couple such vectors to your BRST charge, because then you have a technique to compute the vertices for your Yang-Mills theory. Yang-Mills because you have a spin 1 field, and your vertices will come from the difference between your new BRST operator, let's call it Q. It's modified by the fields of Q prime minus Q of free theory, where you don't couple to any background flat. So let's say it's free. This would be the vertices. So what Siegel and other collaborators did around 2007, if I remember correctly, was to exactly guess a BRST charge that has to be then indeed a good differential, must square to 0 to when evaluated in the right spaces. For Q, I wrote down it's 1 alpha C. So, no, sorry. Lambda square plus I. So this is constructed from the elements of the algebra vector. I'm not doing anything super fancy, but apart from using the covariant derivative, where A mu is one vector field, and the theory is non-abelian, and F mu nu is the field strength. So let me write it in like this. Then we have also the other one, because there are 2 charges, and then maybe there is a 2 here. So,
what is the sigma?
oh yes, sorry. This is the generator of Lorentz part of the algebra. Okay. Actually, of course, the beast here will not square to 0 unless you demand something else. And in fact, Siegel and the others noticed that you might find Q squared to be 0 when you restrict your space of states to be the kernel of another operator, which is again present here because of SO2 symmetry or U1 symmetry that is just exchanging the 2 psi bar, right? You have a possibility to interchange those 2. So with an operator which is a U1 charge. which I'm not going to write down, but maybe I don't think it's super relevant, but you can ask your states to be singlet with respect to this U1, or which is equivalent to say that they must belong to the kernel of this operator. So if you compute Q square restricted to the kernel of J, then this is 0, provided that F really satisfies the Young-Mills equations. So nabla mu F mu equal to 0. And that's it. Yes. So that's something that comes out for free by asking them when you couple your free BRST charge to the background. So basically you substitute for your partial derivatives, you substitute covariant derivatives, you have to adjust then because there is F mu coming from taking the anti-commutator from here. Then this will directly imply that you're working with Young-Mills theory and everything is well defined. Okay, and this is also the case for n equals 4, but for spin 2 fields now, so the gravitons. And this is what Ivo Sachs and Bonetti and Meyer studied in the past couple of years. That namely, if you couple your BRST, your wannabe BRST charge to background fields, which have the same, which are spin 2 fields in this case, then you can find, first of all, that they have to satisfy the Einstein equations, for example. And moreover, then you can also write down the vertices as I just mentioned. I'm not gonna tell you more about the technique of computing tree levels and the loop level amplitudes. It's also possible from this. Okay, so now I just, since I have less than 10 minutes probably, I just want to tell you a bit more about the Ramond fields, because since it has been observed that you can consider n equal 4 in any dimension you want and obtain the linearized Einstein equations or also supergravity equations. We thought, why not also the Ramond fields, because they are also in the gravity multiplet. They are, let's say, the fermionic counterpart. So, of course, you still have a fermionic sector and a bosonic sector in your first quantized theory. And the first thing we did was to construct states by tensor product of two fermions, and this is of course going to work, but these states are not fundamental. I mean, they belong to a Fock space, they don't belong to the Hilbert space. We wanted also a method to have a fermionic operator that creates these states from a bosonic vacuum, let's say, speaking in physical terms. So we looked then at bosonic sector, which is again as before, but also we used the observation from before. Then you can write your variables in your Clifford algebra as with a pair of spinors, theta alpha, sigma mu alpha beta dot lambda by beta. And in general, if I write down something, that doesn't mean that if I give you, okay, sigma mu and sigma bar mu are polymatrices. They are really polymatrices. You will need the fields and entities. Yeah, and in general, if I write down some formula for wannabe Clifford gamma matrices, it's not, I mean, it's just a guess. We are not sure whether this is a representation for the algebra, and in fact it's not, but
So these are two different copies of sigma matrices?
no, it's
Or
this
just the
is,
conjugate?
yes, it's defined as a sigma
Okay,
0
okay,
minus sigma I.
Okay.
Yes.
Yeah, okay.
Yes, so the lucky thing is that in fact it's almost a Clifford algebra. I will write it like this.
Sorry, could you rotate the camera again, please?
Yes, sorry.
To focus on the writings. No, thank you.
Okay, now wait, first I have to write down something else different. Also, we want to have some sort of free operators algebra for theta and lambda, that is the following. Lambda alpha, theta beta, let's say it has to be epsilon alpha beta, and the same has to also for the conjugated part with the dots instead. Dots everywhere. So thanks to this, actually then this is indeed true. This is true. As soon as you restrict this to just some states, say H restricted, where in H restricted, you have to definitely find, sorry. I'm so sorry. So this is parity even. This is parity odd. This is even, so you have to correct with something that is parity odd. Otherwise, you would also redefine your brackets so to be degree shifted, but it's totally equivalent, I think, or at least there is no need to do that as long as you keep care of this degree of the part that I call we call the suspension. So in your restricted Hilbert space, there has to be, since for this you can find you can declare lambda and lambda bar to annihilate your vacuum, while theta and theta bar will create your vacuum. So here you can see that things like this, and this is just something that we found last week, acting on your vacuum. This must be thought as just a degree shifting operator, degree raising operator. And this is a good state, and you have a Clifford algebra, and this is so a nice representation for your gamma matrices. And the same is true if you substitute everywhere the bar part. But you cannot have, and this is also interesting, I think, you cannot have anything like this. And similar things. Right, and the forum conjecture is that this should be the Ramond states, actually, because finally we can have 2 spinors and everything is satisfied. Of course, now one has to check whether they satisfy the closeness condition. It will be nice also if they have these their gauge symmetries that depends actually on the H field, on the Nevauche parts field, right? It's not just they're not just closed forms, let's say but there has to be also some H word as a gauge symmetry. But okay, this is something that we didn't see yet. We didn't check yet. We still have also to construct the modified, deformed BRC operator, BRC charge that has to square to 0, and hopefully it will also yield the relevant conditions for these closed P forms that should be that are the Ramond fields. And I think that this is all I had to say for the seminar. So thank you.
Thank you. Now your Q, you have also like the linear symmetry, like that.
What
So you know, formerly you had this field thing in your Q. Now you have more fields, right?
Yes. Well.
What will you have all?
So we are working with n equal 2 and 4 dimensions. So we have 2 sets. I mean, we have again spin 1 vectors, 1 form, and 2 forms and a scalar, right? So luckily it's not much, but if we had to work in 10 dimensions and then go to the 8-dimensional subspace, then there are many more P forms, right? As we know from string theory. So you can really focus here just again on 1 forms, in fact, but
At some point you mentioned that you did algebra calculations.
This is a work by Ivo and collaborators.
They
Yes.
already. Okay,
Yes,
so
yes.
they used okay.
Einstein's equations and also supergravity equations.
Oh,
For G, the two forms, I mean the Neveu-Schwarz free
okay.
and the Dirac. Yes.
So one more question from me. Before you were restricting to some subspace in your Hilbert space, which was whatever was spanned by two psis, was that the right thing? And now you're saying it's even more restricted, right?
Yes.
Okay, and that doesn't spoil the previous conditions on the spin one fields in the BRST closeness of the Q operator.
I'm not sure one should work even there with this representation and check this, but I think it's not really the point this moment. Like we just want to use this representation to have something that can be thought as the Ramond fields. So, and in 4 dimensions, there will be a one form then.
I see. And what do the vertex operators for those RR fields look like? Is it just something in terms of the lambdas, or do they have no in terms of capital thetas, or times the appropriate form?
I'm not 100% sure because I'm not an expert, but I think so, yes. Maybe Ivo can answer the question if he is still there. I think so anyways.
No more questions from the
I don't think so.
Thank you. Sorry for too many questions.
No, thank you so much. You're an expert. It would be nice to have you here in Prague. Why did you leave us? Okay, maybe I should stop recording.